Welcome to the Explainer. So today we are unpacking some source material that is honestly mind-blowing. We are looking at a remarkable 4,000-year-old cooling system that can actually outperform modern air conditioning in extreme heat. And the real kicker here? It does all of this using zero chemicals, zero compressors, and practically zero electricity.
Okay, let's dive right into this. Just think about the staggering contrast we're looking at. On one hand, you have the standard approach, a massively complex, grid-dependent mechanical AC unit that easily costs $5,000 to install. On the other hand, a $50 stack of wet, unglazed clay pots. No Wi-Fi required, no firmware updates, nothing. It's this fascinating standoff between a $100 billion HVAC industry churning out really expensive plastic boxes and an incredibly cheap earth-based alternative. Which naturally brings us to the ultimate question, right? If a pile of wet clay works so incredibly well, why aren't we all using it? Well, throughout this explainer, we're going to unravel the mystery of this lost technology. To do that, we need to take a pretty fascinating journey through ancient history, dive into some hard physics, and objectively look at the modern economic structures that kind of dictate how we build our homes today. We'll start our investigation with Section 1, the ancient desert secret, survival in 113-degree heat. Way before we had modern machines, builders in places like Persia and Egypt regularly faced just blistering temperatures. And tracing the history here shows exactly how they engineered survival. By 400 BC, the Persians were already building massive, 59-foot mud brick domes called yakchals. These things utilized subterranean pools to literally manufacture ice right in the middle of the desert. Jump ahead to the 16th century, and you've got Mughal Emperor Akbar manipulating temperatures way before the electrical grid even existed, using these complex Himalayan ice relay systems and specialized cooling rooms called the Abdar Khana. And this wasn't just for ice storage, it was seamlessly integrated into everyday living spaces. Think about the Middle Eastern mashrabaya and the Indian jali. These were beautifully ornate, perforated screens designed to cool entire palaces using absolutely nothing but earth and wind. But the source material makes super clear is that cooling with mud and water isn't some fringe alternative. It's a highly resilient, proven technological heritage that was just sort of systematically marginalized when chemical refrigerants hit the scene in the 20th century. Which brings us to Section 2, the physics of wet clay, how Earth steals heat. To really understand why this ancient logic still works so flawlessly today, we have to look at a single, extremely elegant law of physics, evaporative cooling. Simply put, when water changes from a liquid to a gas, it requires energy. So in this setup, the water consumes that thermal energy directly from the surrounding hot air. It's literally stripping the heat right out of the room. Now, what's really interesting here is exactly how the material enables that evaporation. The clay absolutely has to be unglazed terracotta. Because it's unglazed, it retains millions of these microscopic channels. Through a process called capillary action, these pores act like a vast network of tiny little pipes, automatically pulling water evenly throughout the entire body of the clay. This makes sure the cooler is constantly covered in a super thin, highly efficient film of moisture. But the real magic, that happens when you shape the clay. If you just have a flat, wet wall, the air kind of bounces right off. But if you stack terracotta tubes into a brilliant honeycomb geometry, you massively increase the surface area. The hot air gets pulled in, and those circular shapes force the air into this tight, spinning turbulence. That spin is totally crucial because it forces virtually every single molecule of air to physically strike the wet walls, transferring its thermal energy straight to the water. Oh, and we definitely can't forget the Venturi effect. Because that incoming air is being squeezed into those narrow honeycomb openings, its velocity suddenly shoots up. This faster-moving air makes the water evaporate much more quickly, dropping the temperature even further. The end result? A dense, chilled breeze exiting the stack that can be up to 27 degrees Fahrenheit colder than the blistering environment outside. Absolutely incredible. Plus, there is this wonderful sensory bonus here that really grounds the physics lesson in the human experience. The system acts as a natural filter and adds this gentle humidity, which produces petrichor. That's that amazing, distinct, earthy scent you get when rain falls on dry soil. The sources highlight that this scent actually has a documented psychological impact on our brains, genuinely lowering our perception of heat and giving us this deep, natural relief that a plastic chemical unit just cannot replicate. Moving right along to Section 3, the modern beehive revival, cooling and industrial heat island. Back in 2017, an architect named Manish Siriparapu led this fascinating revival project at an electronics factory in New Delhi. This factory was facing a massive crisis. The exhaust from a huge generator had created a localized 122-degree Fahrenheit heat island. Traditional mechanical air conditioning completely failed. It just couldn't handle that kind of localized, extreme thermal load. So Manish looked to the past. He combined the ancient geometry of the beehive with traditional claycraft to build a modern terracotta cooling wall right in front of the exhaust. And the results were a staggering success. The terracotta stack took that blistering 122-degree air and dropped it all the way down to a highly manageable 97 degrees Fahrenheit. That is a massive 25-degree drop, and they did it using essentially mud and water to fight off industrial generator heat. And this brilliantly illustrates just how incredibly efficient this whole system is. Energy data from the project showed a massive 80% reduction in energy consumption compared to traditional mechanical AC. The entire installation ran on less than 0.63 units of energy per hour. To put that in perspective, it provided industrial-strength cooling for less than the cost of running a few household light bulbs. Section 4. Why is it ignored? Market and structural barriers. So, to understand why this isn't in every American home right now, we do have to objectively look at the limitations. First off, there is a climate limit. Physics dictates that it's just ineffective in highly humid areas because high ambient moisture stops the water from evaporating. Second, having a permanent open-air structure poses a real risk of heat loss during the winter. But honestly, the biggest hurdles are regulatory. U.S. building codes generally require what's called a sealed envelope model, meaning homes basically have to be airtight. This legally excludes breathing systems like this from being used as primary ventilation. And finally, there's the economic split incentive. A landlord just isn't going to invest in highly efficient cooling if the tenant is the one stuck paying those high utility bills. From an industry perspective, the reality reported in the sources is pretty stark. The global cooling market totally relies on a cycle of high-margin sales and planned obsolescence. Think about it. Air conditioners are these complex machines with hundreds of moving parts that constantly need servicing, and then total replacement every 10 to 15 years. Economically speaking, there is literally zero recurring revenue in a stack of clay pots that easily lasts 50 years. The modern HVAC industry simply isn't designed to profit from a one-time, low-cost pile of earth. All right, our final section. Build your own cooling wall, the open-source physics of the beehive. Because the physics of this system are completely open source, the barrier to entry is remarkably low. If you want to reclaim this technology, you can literally do it yourself today. Here's the DIY flower pot method outlined in the sources. Step 1, you must source unglazed terracotta pipes or just standard garden pots. That unglazed part is absolutely non-negotiable. If it has a shiny, decorative glaze, the pores are sealed up and it will not cool. Step 2, arrange them in a honeycomb pattern inside a simple wooden or metal frame. Step 3, place a small 12-volt fountain pump in a water reservoir at the base so it trickles water over the top. Now the brilliant part is connecting that pump to a small 20-watt solar panel. By doing this, the pump naturally works harder right when the hot sun beats down, perfectly scaling your cooling exactly when you need it the most. Of course, if you're looking at a larger, more industrial scale, the sources note that Ant Studio now offers specialized modular facade designs. Their work has sparked this whole global movement of makers and architects adapting these modules for diverse climates. And if you want hands-on training, organizations like the Center for Science and Environment provide really comprehensive workshops on passive cooling and vernacular building techniques. So as we wrap up this explainer, I want to leave you with this provocative thought. Are we truly trapped by our dependence on the electrical grid and expensive plastic machinery to stay comfortable in a warming world? Or are we just forgetting our own history? It's incredible to realize that sometimes the absolute most sophisticated solutions for our future are actually 4,000 years old, just waiting to be rediscovered in the earth beneath our feet. Thank you so much for exploring this with me, and keep questioning how things are built.